guess it works.
Okay, and the point is in the middle.
Yeah.
So, okay, good afternoon. So the first speaker of this afternoon session is Philippe Thielin from University of Bordeaux, and he will speak about classification of calibrated configuration and effective potential for a quasi-periodic environment.
Okay, thank you very much. Thank you, Rodrigo, for the invitation, and especially also for the opportunity to work with some of your students that actually I don't have in Bordeaux, so good students. Yes, Gregorio, maybe you know from some years ago, and now Enrique, he's not there. Enrique Corsi. Okay, so that's a subject I did with Eduardo Garibaldi at Unicamp and Stéphane Petit at Amiens, France. Okay. Okay, so just two parts, and the first part I would like to explain what is more or less the theory of Frankel-Contorda, and in the second part I will explain what we did new in this problem. Okay, so what is this problem? So let's say physically we consider a metallic gas that we want to deposit on a thin layer on a substrate, and we want to create a thin layer of this metallic gas, and the substrate is periodic, and we want to understand how the particles of the gas are positioned with respect to the atoms of a, let's say, crystal, if we have a substrate of crystal type. So in this picture, the black dots, which are the position of the atoms of a crystal. Oh, sorry, this one, the black dots. So let's say that I have chosen a unit which is 1, which is the unit between two atoms of a crystal. And the red dots are the atoms of the gas that we want to lay down on the substrate. So the forces, there are two kinds of interactions. You have the mutual interaction between atoms, and we will choose a very simple interaction, let's say between two successive atoms. And this is like a string force, so a very simple force. And there is also an interaction between the metallic atoms and the substrate. And since it's periodic, the usual theory, the periodic setting, is that the potential you give is, in addition to a potential for the string of force, is a periodic potential. So this is summarized here. So we have a mutual interaction between two neighbors and a periodic external interaction with a substrate. Okay, so that's the usual Frankel-Contorda theory. So here I assume that the substrate is infinite. A priori, it would be much more interesting if it's a two-dimensional object, but we are unable to do this. So we work with the 1D object only. We think that the metallic atoms are ordered, so we can index them. So that's why I can use the index Z, and the position of the atoms are given by this number xn. So here I have two potentials to define the total energy. So W, which is the mutual interaction, and V, which is the external potential, which will be periodic in the classical Frankel-Kotorba. Exactly. These xn are the position of the atoms of a gas, because the crystals is just are positioned by Z. So I have chosen 1 for, let's say, the unit for this no physical distance, yes, just 1. Okay, the Frankel-Kotorba is given by this, so the mutual interaction is given by the elastic force. But you have this lambda, which is very important. I will come back. And you have also, let's say, a periodic function, and this is the simplest periodic function. And I choose everything positive to simplify, although you can add a constant to the energy, it does not change. So here everything is positive. So lambda is important because it's the mutual, it's the distance of two atoms of a gas when they are at rest. If there is no V, if you minimize this, W, then you get 0 when Y equals X plus lambda. So the distance has to be lambda. So you have a string where at rest, the length is lambda. Okay? And V is the periodic force. In front of V, there is your coupling, which means that you may have two, let's say, you may have two different behaviors, whether kappa is extremely large. So if kappa is extremely large, when you minimize the total energy, which is W plus V, you have, you minimize V, and it has to be when 1 minus cosine equals 0, means that X belongs to the position of the atoms, of the crystals. So you are attracted by the atoms, yes? Yes, W. No, exactly, but I think the idea is you have a very thin layer, so you just study this layer, and this layer is just one layer of one piece of atoms. Mutual interactions, yes, you are right. It could be, let's say, long-range interaction. We don't do this. We just take the nearest neighbors. Yes, exactly. So that's, you are right. It's an assumption, but it's the assumption of Frankel-Kotorba. It's not so easy even to put n plus 2, n plus 1. Yes, just short range, but not n plus 1. So we are just like in the Ising model, and it's, yes, it's yes, you are right. In a gas, yes, but the gas, okay, we are at which level here? We want to freeze the system and make this thin layer. So we are at 0 temperature, so we are not in a gas with positive temperature. We don't study this, we just study the ground configuration. So I was coming to this problem. So compared to what everybody has said here, so you put a positive temperature and you want to understand, yes, let's say, the equilibrium at fixed temperature. Here we are at 0 temperature. You can expect this, and you can expect that they are ordered. Actually, it's not clear that they are ordered. Already this problem is not so simple. So which means that if they are not ordered, there is no sense to take the neighbors, because if you mix them, the neighbors could be at the neighbors of xn in terms of distance could be xn plus 10. If they are not ordered, there is a problem in the, let's say, in the modeling. But actually, they are ordered. So it's consistent. Okay, so just want to explain that they are, let's say, a strange behavior in the sense that if kappa is very large, then xn has to be z to minimize v. But if kappa is very small, let's say 0, if you want to minimize the mutual interaction, you have to be, xn has to be n lambda. So if lambda is not an integer, is rational compared to 1, so it's rational, then there is a problem, a competition between two phenomena, one which minimizes W and one which minimizes V. So here, I will come back a little bit after this, after the talk, but we are really at 0 temperature. So of course, that would be interesting to define something at positive temperature, but you could say it's obvious, the problem, but for you at 0 temperature, the set of ground configuration is very small, let's say plus, 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 or minus, minus. Here, it's exactly the opposite. The set is extremely big. It's like an object of a degree of freedom 2. So you have, it's a continuous, you have a continuum set of ground configuration. So that's why the first thing to study is the set of ground configuration, and after you want to really understand how you freeze a system, how you put a temperature on this problem. Okay, questions? We want to understand the set of ground configuration, which means we want to understand, so what is a configuration? The configuration are the position of the atoms of the gas, let's say, a thin layer, the position of the atoms. So Xn belongs to R. So in your language, we have unbounded spin system with value in R. So now we have this total sum, which is infinite, of course, and we want to define what is a ground configuration. So this has to be defined. Okay. So I explained the two competition in the Frankel-Cantorova model. So lambda is a very important parameter, actually, in general. So now what I am going to explain is first recall or define the notion of ground configuration. Now, of course, you could define also ground states, means translation invariant probabilities. So here there is a problem that do we have probabilities? Yes, because we have, let's say, the cell, the periodic cell of a crystal. So this is, let's say, this is compact, although we have unbounded spin, so it's uncompact. So maybe there is a problem to define this invariant probabilities. But I will not discuss this. I want to discuss only ground configuration. And actually, that we have done, in addition to the usual Frankel-Cantorova, is, okay, we suppose we have not really a crystal, but a quasi-crystal, which is perturbed by some impurities. So do we have the same result? So this is the question we want to solve today. How to perturb a little bit the Frankel-Cantorova means how to perturb the potential V. V will not be any more periodic. It will be quasi-periodic in some specific sense I will explain. Okay. Well, there is a symmetry which is destroyed if V is not anymore periodic. That's why the problem becomes very difficult. Is that if you have a ground configuration, you can shift by 1 everything. So if you shift by 1, you see 1 minus 1 disappears, and V is 1 periodic. So you get, again, a ground configuration, which means that if you have a ground configuration, and you shift so that you see all positions on the cell, the unit cell 0, 1. So you have a lot of, you may have a continuum set of ground configuration. That's something that disappears if V is not anymore periodic. And that's the problem we had to face. Okay, so there are actually many notions of how to minimize such an energy, which is an infinite energy. There is, let's say, a weak sense, because we call it minimizing configuration, and this is the sense you can, let's say, define on any dimension, so on a Z2 lattice, on, let's say, a standard Hamiltonian defined by, let's say, many bodies interactions. This could be defined, and there is another one, which is a strong sense, which is called here calibrated configuration. I will explain this in dimension 1. So dimension 1 means that we understand the position on R. We don't on a plane, so that we cannot do. So that's why. And on R, we can define another notion, a stronger notion of minimizing configuration. So here, the first, let's say, definition is the weak sense. So now you have, let's say, two notions of block. You have a block given by the value, the observable you see, and which are the distance, the position of the atoms. So you look at a block where the position of the atoms, metallic atoms, where there is no anymore substrate here, it's periodic. The positions are in an interval AB. And you assume that you take another block of indices. That's why you have, let's say, two kinds of blocks here. Let's say you start at x0, xb, or you start at xl plus k. So you have a block of indices and also a block of values you observe. And you assume that when you start, x0 is at the left hand point and y at the right hand point. Okay, so you fix the left and right, A and B. You look at a configuration, so you say that the blue configuration is minimizing if you can only increase the energy, so by taking another Y configuration, a red dot. But here, you have exactly the same number of particles in this interval AB. So you look at K particles, here you have K particles. The blue dot minimizes this energy. If you perturb a little bit, but not the number of particles, you just increase the energy. So you call it minimizing. And this could be defined on any dimension. This is it's well known, provided that you fix the boundary. So you have a block of indices, you fix the value at the boundary, and you can only increase. So this, at least in any dimension, this can be defined. Okay. Now the strong sense is more interesting, because the question at the end is, can you find minimizing configuration? Okay. Can you find this? So yes, you can, because you can also find stronger minimizing, which we call calibrated configuration. So what is a calibrated configuration? Well, you say it's calibrated if there exists an effective potential U that calibrates. Okay, what is an effective potential U? That's the picture here. So you want to create a force so that when you cut the string, when you cut the configuration and you look at, you cut the left-hand part, the potential gives you a force so that if you cut it, then applying this force, the configuration stays at rest. You don't change the configuration with this new force. So you see, this definition strongly depends on the fact that R is ordered, because I am discussing left and right. Although there is an extension where it's like in fluid mechanics, where you have the tensor, a stress tensor, which gives where you define the force if you cut the fluid, and you look at the force you have to apply to a plane so that the fluid stays in rest. So there is also an equivalent definition in higher dimension, but this I am completely unable to do some, let's say, mathematics after this. So this is just, let's say, a picture to explain what is U. So of course, now you have this U on the, left-hand side, which defines this force. Then inside this box of AB, so AB are the values you see, the position. Then you put any particles here, and of course you should obtain at the right-hand side the potential U. So which means that you count the energy inside the box. But actually, if you do this, the energy in the box is additive. So you would get something which is linear in the size of a box. So you don't want this, because you want a U which is periodic. So you have to renormalize the energy you count in this box, which is a kind of relative energy of, let's say, the initial total energy in the box minus some fixed energy, which is called effective energy. So So in addition to find U, you have to find E bar. So U is called effective potential, E bar is called effective energy. Okay. Now, more formally, mathematically, what is an effective potential? In the periodic case, U will be periodic if there exists an E bar. Now, you see the difference of the potentials between two values, to a block of an interval where you look at all the values. Imagine you put just two particles on A and B, and the formula I had before is just exactly this before, this one, where k equals 1, you have only two particles, then you just get exactly W minus E bar. So you need an effective energy so that UB minus UA is really the smallest energy, relative smallest energy, and given for every A and B, but if I choose B, which is on the right-hand side, then there exists an A which realize the infimum, realize the equality. Otherwise, you could have another definition where this is true for every A and B, but the second equality is not true. So it's U is minimal among all U satisfying the first inequality. Well, this definition of effective energy has been defined by Griffiths and True, physicists, a long time ago, also related to Frankel-Cordova and Aubry theory. But actually, it has other names. In homogenization theory, it's called corrector. And actually, it's also used in Lagrangian dynamics, where you have a Lagrangian for, let's say, a special Hamiltonian, which is tonally, which is strictly convex. And for this system, you want to understand paths which minimize the Lagrangian. So it's, again, a minimization problem. If you discretize the time, you exactly get Frankel-Cordova. But in this theory, where you have continuous time, so Z was the time, the lattice Z was the discretization of the time. In this, here the time is R, and it's called Wickham solution. So it has many names. Okay. Now, a configuration now formally is U-calibrated, means the strong sense means that if you take any configuration xn, now you take two indices, xl and xl plus k, so L is anything in negative positive, k is positive, then the difference is the sum of the relative energy. So you see in this term, you have k atoms and you have k E bar. So this is, let's say, the effective energy of a block with k atoms. It's k times E bar. And, but it's just, you want to compare with this number, and actually the difference is exactly the difference of a potential. And of course, because we have, let's say, the inequality here everywhere, then you have also an inequality here. And this is very different from before, because again, you take a box of observed values, A and B. The blue dots are the calibrated configuration. So they start at A and end at B. And now you compare the relative energy, which is W plus V minus E bar, of another configuration, the red dot. But here, the number of points is anything, provided that you start at A and you end at B. You can only increase. So it's, of course, it's a stronger definition, because before the number of red dots was equal to the number of blue dots. Okay. Well, what is compact here is the fact that each time you have a, let's say, a configuration, you can shift so that, let's say, you look at the cell 0, 1, the periodic cell. But then there are two problems, if you want. Even in the periodic case, when you want to minimize and get such a ground configuration, the interdistance may grow. It's not anymore compact, this. So you have to prove that the interdistance is bounded, uniformly bounded. Yeah, but the interdistance xn plus 1 minus xn is bounded. So this is uniformly bounded, and then it's compact. But just this question to prove it's uniformly bounded is not obvious, even in the periodic case. And if it's not periodic, we lose this compactness. So that's why it's a difficult problem. Okay, so I said that configuration is minimizing, so it's a stronger notion. Also, it's difficult to find an effective potential, and actually we spent a lot of time to find this in a non-periodic case. But actually, there is one definition, an intermediate definition, which is between, let's say, minimizing and calibrated, which is called Magnier potential, because Magnier studied Lagrangian dynamics. So this comes from WKM theory, and which is a kind of barrier between two observed values, A and B. So you want to measure the cost you have to spend going from A to B. A relative cost, because again, you count all, let's say, you take an infimum, you take any numbers, any particles, starting from A and B, you measure the relative cost of this block. So K is anything, so it can grow to infinity. But the relative energy is actually bounded from below. And you can define a function, and you call it the Magnier potential. And you say you are calibrated with respect to Magnier because your configuration, if you compute it, you start at XL, you take any L, you start at any point of your configuration, you end at any point of configuration, you have K points, and the infimum is exactly equal to the sum. So this is just to rephrase, there is no U here. That's what the purpose of the Magnier, there is no U. So before you are able to define the U, maybe it's better to study the Magnier potential. So that's this definition. Okay, so let's I want to say that the Frankel contour belongs to a family of interactions, so it's not just related to this. So to simplify, I again write W plus V, but actually, so W, remember, is the elastic term, and V is periodic. Actually, you can define any E0, xy, not necessarily equals to W and V. You have to add a parameter, but you see it's a linear parameter. When you develop this, you get a linear parameter. And actually, this is important because then you include this family in a one parameter family, depending on lambda. And what do you ask? You ask C2, you ask uniformly Lipschitz. Okay, that's not very strong, this, with respect to y minus x. Well, we are in the periodic case, so if you add +1 to everything, you don't change E, okay? And that's the thing that actually Aubry observed is the twist condition. So if you take any E satisfying the twist condition, you can say you are working with the Frankel contour model. It's the same model. In addition to this, you add the superlinearity condition, which means that if two particles are far away, the energy grows superlinearly. This is not good because you would prefer a potential like the Lennard-Jones potential, which goes to infinity, to 0 at infinity, but which prevents particles to go close together. So this is the lambda, if you want, in the Lennard-Jones. So you could do Lennard-Jones, actually. But let's say I am in a very simple case. In Lennard-Jones, you have still a whale. So I want a whale. And of course, to simplify the proof, if your whale also extends to infinity, that's better. But it's, let's say, could be avoided. The twist condition cannot be avoided. Okay, so here, just to say that we are at the 0 temperature level. We study unbounded system. We have periodic one-body interaction. So we could define for the D lattice, no problem. We could also say that the value we observe is not R, but is RD. Let's say, at least everything can be defined. And, but here, because we want to study calibrated configuration, we need D equals 1. And actually, we observe real values and not R. So it's very specific what we are doing. Okay. Another remark is that it's not so simple, the problem, because we come back to Cherenkov map. So again, a minimizing configuration, you can just take three particles of a gas, of a metallic gas. And you just say that you minimize xn. So you just fix xn minus 1, xn plus 1, you minimize xn. So you need to be critical in this sense. Okay. And this defines a twist map because you can think E as a generating function, discrete generating function. You can think Xn as the position. You can think Pn as a momentum. And usually you define the momentum like this, minus and plus. And from this you get a map. Now, here is the compactness because you can say Xn is defined modulo 1. Implicitly, with Pn given, you get Xn plus 1. And from Xn and Xn plus 1, you get Pn plus 1. So you define a map, which is, let's say, C1. If you start with C2. And for Frankel-Kontorova, you get the standard Cherenkov map, which is highly chaotic. And we even don't know if it has a positive entropy, for instance. So that's the space of critical configuration, not critical. Inside this space, you have minimizing. Minimizing, you have a lot of minimizing configuration, means that they have order. They go to infinity plus minus infinity. They have rotation number, and any rotation number is achieved by configuration. So you have plenty of minimizing configuration, at least parameterized by their rotation number. But you have only one calibrated configuration, and the lambda appears here. If I have some time, I will say something about this. Okay, old and new result. So let's recall that we have a model of this form now. In order to be simple, I prefer to fix E as a W plus D, and I include a parameter, minus lambda, linear. The old results are for periodic, and the new result that I am going to explain is for quasi-periodic. Okay. I assume C2, and the twist and superlinearity means that I have a strictly convex. So it's an assumption which is convenient, but not so fundamental. Which is fundamental is convex. Convexity is important. Yeah. So we cannot do, let's say, the double wave for W. The double wave, we cannot do it. Something like this is impossible. Okay. We want to understand ground configuration, even minimizing or you calibrated. Okay, so now remember to define an effective potential, we have to also to define an effective energy. But in order to guarantee that this number has a meaning, so it's unique, a very unique effective energy in the system, then you ask that the effective potential, if you are not in the periodic case, you ask at least it has sublinear growth. Because it's easy to construct linear growth, but as you will see, it's impossible to define a really unique effective energy. So this is the assumption we ask in the non-periodic case. If V is periodic, actually U is periodic. Okay. And again, rewrite the equation of U that if I take any Y, then U, you remember they have two inequalities, less or equal, or the infimum is achieved. So you just say that given Y, there exists an X such that you add U, which is on the left, you add the relative energy, E minus E bar, and you get the U on the right on the box XY. Okay. Okay, I simplify the notation of this sum of the energy of a box. So I didn't really use the standard definition of the free energy, the free Hamiltonian, sorry, of a box of index k plus k 0 n 0 n, because if you look at carefully here, something is missing. There is a one-body interaction on the right which is missing, but we are in dimension 1, so it's not important to forget this. So it's between a boundary and a free Hamiltonian, this notation E. Well, what is the natural candidate for the effective energy? You take any finite configuration, you compute the energy, you take the mean, and you take the infimum, and you take a limit. This limit exists easily, and this should be E bar. Okay, so in some sense, I have no choice for E bar, although if I don't require U, the effective potential to be sublinear, is not unique. So first of all, remember that U satisfy this equation here. So I can define an operator which is called Laxolinic in other languages, in let's say in homogenization theory. You can define such kind of Laxolinic operator where given U, a function, you take the minimum, so given a point y, so you get, given you define a new function, tu, at this point y is obtained by minimizing in x, u plus e of xy, y is fixed. So that's a nonlinear operator. If it's periodic, so that's the standard, the old theory. For V periodic, there exists additive eigenvalue, lambda, and an additive eigenfunction, u of this equation. So it's very close to the standard theory of positive matrices where you have a unique largest eigenvalue. We are very close to this, but it's in the additive case. It's not multiplicative. But actually, because U is periodic, in the periodic case, lambda is unique, and actually there is a unique eigenvalue, and lambda has to be equal to this E bar. But there are many U, there are many effective potentials here, even in the periodic case. It's related to the Mather sets. I will not explain this. This is related to the translation invariant measures of this system. Now, recall what is U calibration. So you want to say that the difference of U at two along the configuration, and you see the position XL and XL plus K, and this is exactly equal to the sum of the energy, the relative sum. You subtract, because you have K term between XL plus K and XL, so you subtract K E bar. And if you take any other configuration, you see I don't take the same indices, I take any I, any J, the difference is anything, not comparable with respect to K, and just can increase. That's just recall the definition of calibrate. So now, assume V is periodic, and if U is an effective potential, then there exists calibrated configuration very easily. This is the next slide to show that the advantage of an effective potential to obtain configuration, actually calibrated configuration. But something is a little bit strange. So even in the Frankel-Cordova model, so which is here, if you choose lambda, so lambda, remember, is the interdistance between two successive atoms. If lambda is too small, then actually, compared to kappa, then there are calibrated configuration, but they are all located in one cell. So it's completely not physical. Everything, you have infinite number of particles located in just one cell. Okay, so you have to be careful, but mathematically it's what you get. Okay, and the algorithm to obtain the calibrated configuration is easy. You take anything, x0, then you solve your equation backwards. I mean, you take x0 is fixed, you minimize this expression, you get x minus 1, you put x minus 1, you minimize again, you get x minus 2, so you get backward calibrated, but half. And to get something not half, be infinite, you just shift everything, and you use periodicity to be able to, after shifting, by coming back to a unique cell 0, 1. So let's forget this. Now let's discuss the almost periodic case. That's the new subject. So now V is not periodic. So let's say you may think almost periodic, not quasi-periodic. So what's the difference? Almost periodic is because you add many cosine with frequencies which are, the ratio of frequencies are not rational. So you have incommensurate frequencies. And in this case, well, if you perturb lambda equals 0, so if lambda is small enough compared to the two constant, coupling constant kappa 1, kappa 2, then, okay, the natural energy is, effective energy is 0, but there is no minimizing configuration. So it's not obvious to extend Frankel-Kotorova to non-periodic potential. That's just the remark here. Although a crystal is not a crystal, is not perfect. So why it's true now? Why you can do the same thing? So that's why we define a new notion. Actually, well, it exists in physics. You want to say that your substrate is quasi-crystal. Okay, what is a quasi-crystal? Of course, a mathematical quasi-crystal. It's a crystal modified by impurities, but the impurities are distributed with very low complexity, certainly not IID, and even the almost periodic case does not work. So this, although it has 0 entropy also, but the complexity is too much. So you want to understand the complexity in terms of patterns of impurities, and you want to say that the patterns actually, all patterns you see repeats actually linearly, but actually repeats. So that's a notion of patterns that you see many times along your crystals, the patterns of the impurities. So that's, I am going to explain this on, let's say, I start with a sequence, a symbolic sequence with 0 and 1, and to simplify things and to have an example of a linearly repeated sequence, I start with a Fibonacci, which is a substitution. I have two symbols, 0 goes to 1, 1 goes to 1, 1. I take the square, 0 goes to 1, 0, 1 goes to 1, 0, 1. And from this, I can define fixed point. So fixed point means that, let's say this one, you have to start with a word. If 1 is given, the iteration is 1. Yes, 1, 1, 0. So you see 1 repeats. So that's why you get a fixed point by just repeating this word many times. So this 1 goes to 1, 0, 1, goes to 1, 0, 1, this is the next word, next one, and so on. When I repeat sigma 2, sigma 3, sigma 4. To do a bi-infinite sequence, symbolic sequence, I have to start with two symbols here, either 1 or 0, and I look backward. So you see 0 here starts or ends with 0, and 1 ends with 1. So if I iterate 1 backward, 1 goes to 1, 1, 1, 0, 1, and next, and next, and so on. So I get a fixed point of sigma square. Here I have to use sigma square, and this always exists for substitution. Okay. Now I want to define the geometric setting, because this is just a symbolic setting. So I start with my Fibonacci word here, and I want to associate lengths. So I have two symbols, 0 and 1. I have two lengths, two different lengths. So now, and the Q0 on this picture are the impurities. And I want to distribute the Q0 according to the Fibonacci sequence. So Q0, let's say it's at 0, and Q1 corresponds to a symbol 1. So remember, I have 1, 0, 1. And here, I have a length L1. And on this length, I put a potential V1, which is smooth. I want to be smooth, C2 smooth together. So let's say a potential like this. Now I see 0, so I put a potential the blue one, I see 1 on this world, I put the potential on the length L1, V1, and just repeat. So I repeat a potential, let's say V0, V1, according to the letters of the Fibonacci world. It looks like periodic, huh? So it's my quasi-periodic potential here. Okay, so why? Actually, we don't use substitution. We work with sequences, the infinite world, and the main term, the main observation on Fibonacci is the fact that it's a repetitive. So what does it mean? It's a repetitive. If you take any admissible pattern, what is a pattern? Admissible pattern is a subworld finite you see on the infinite world. You call it P, and from this P, you can find a length MP depending on the pattern, so that any box, any pattern, any subworld of length MP, C contains the pattern P inside. So for every MP, index MP repeated, you see a specific pattern P given at the beginning. So it's called the repetitivity. Formally, you can define the hull, and the hull is compact, and the hull is actually minimal. This is another way to say that dynamically the hull is minimal. This could be done. I mean, the notion of pattern like this could be done in any dimension on the plane, and there is another word which is called, let's say, Delaunay sets, or let's say tilings. So we are in the tiling theory here. But here it's 1D, so in 1D it's easier to explain. Okay. So there is another example of sequences. So you take alpha between 0 and 1, and you take the integer part of n plus 1 alpha minus n alpha. It belongs to 0, 1, and you get the Sturmian sequence. And it's, again, I'm sorry, I forgot, the lemma, the Fibonacci or the Sturmian sequence are linearly repetitive. What does it mean, linearly repetitive? It means that the times you have to wait to see exactly the pattern P depends linearly with respect to the size of the pattern. And this is the assumption we ask for our main result. So we have, again, another additional assumption, which is the non-degeneracy. And which means that the minimum is not the effective energy. Why? Because if the infimum equals this, immediately you have a calibrated configuration, which is just x fixed point, which satisfies the equality here. So it's very degenerate, could happen. It happened in the counterexample I gave you for Frankel-Cordova for small lambda, but it happened. So we want to avoid this, okay, so we assume this. And again, we assume V is quasi-periodic and linear repetitive. So that's now the new assumption. Now, the intermediate result, because I cannot state everything in one theorem, but it's what you have to prove before, and it's very, let's say, satisfying. Any calibrated configuration is strictly monotone and unbounded on both sides. So, okay, so it's for the modeling is good. You have also, if you look at, so it's strictly monotone. If you look at the interdistance, it's between small r and big R. It's also good. It has rotation number, and actually for periodic case, it's more than rotation number. They are close to the linear the line of slope rho. And also, we discovered something which actually we didn't know even in the periodic case, that we have a preferred ordering, which means that if we are trying to understand calibrated configuration, either they are all increasing or either they are all decreasing, and this gives an ordering. So I will give you pictures for the positive ordering where all calibrated configurations are increasing. Yes, why for Frankel-Cordova you could decrease? You just change the sign of lambda. So if lambda, it's mathematical, lambda it could be, for you is a distance, but could be negative, then you just, let's say, change the axis of x, and everything goes to minus infinity. So that's why in mathematics, let's say. Now, the theorem we had obtained with Garibaldi and Petit, so there exist calibrated configurations. So as in periodic case, there exists effective potential as in the periodic case. Now, and this is without the linear repetitive condition, assume it's linear repetitive, then all effective potentials are of the three types, and they are non-empty. So either it's sublinear, so finally, let's say we were happy to find effective potential with a sublinear growth, but there are two types, and I will give you a picture, and I will stop. Here are the three types. Sublinear growth means it's like log, so I put a log on minus and plus infinity. The overgrowth is this, so you are bounded from above by something with a slope, bounded from below by a slope, a positive slope here, a negative slope here. And the other types, the third type, is mixed between this picture and this picture. So as you see, the one where the slope is positive does not exist. So this type does not exist, for instance. Okay, so actually we wanted to do something. We wanted to prove that there are bounded effective potential, not periodic, but bounded at least. We were unable to do this, although for, let's say, the substitution case, we are able to say that it's bounded at many points, infinitely many, going to infinity, but it's not bounded, and we are not able to do this, so it's very low. I mean, the result is just this. Of course, there's something more interesting, even in 1D here, so everything in 1D, is to understand how, when you freeze really a system, how you go to this ground configuration. And this is how to put a temperature on the system. It's strange, but this has never been done. Well, although I know that you work hard on Gaussian free field or Gaussian field, but it's not, even if I take x minus y. Because usually either it's let's say, massless, okay, or massic, but massic means the potential V of x is x squared. So you have only one well, and here we have a periodic well. And actually, okay, it's not done. Maybe you could say more to me that it's not done. Yeah. So that would be interesting to put a temperature and also see the limit, or let's say, if not, no limit when the temperature goes to zero. Okay, thank you.
Okay, wait.
Oh, thank you very much for the nice talk. Right, so yeah, the first thing that I was going to ask was actually about whether there is a version with a temperature. But even without, do we know anything about the, like, right, so like, sorry, could you go back to one of your last results where you say about the spreading of them being equal to, no sorry, a bit before that.
Before?
Yeah, the limit of x and, yes, that one. Sorry. Do we, is it anything known about, like, if now I subtract n minus p, like what is the size of the fluctuations essentially?
Yes. For the periodic case, xn minus n rho minus x0 is uniformly bounded. Here we don't know.
Okay.
And this is true for any minimizing, which is a big set. And I have to explain why, because in 1D, a minimizing, so you remember you have to include the Frankel-Kotrova in a one family of interaction. There is this lambda. It's a linear term. You would say, okay, a linear term compared to the quadratic is not important. But actually, this is, and if you come from, let's say, the Lagrangian theory, this is a closed form. So you add a closed form. When you add a closed form to the Lagrangian, the Euler-Lagrange equation does not change. So you don't change the dynamics. So this lambda does not change the dynamics. But it changes the calibration because you have to compute, you have to minimize energy. So the result is that in 1D, is that any minimizing configuration for, let's say, lambda fixed is actually calibrated for another lambda. Okay. So you always come back to calibration, but you have to change the lambda. And which means that for calibration, this is easy to prove, but the fact that you are bounded, xn minus n rho is bounded, and this is why it's true for any minimizing configuration. For quasi-periodic, I don't know.
Thank you very much.
So thank you for this talk. I have a question related to this theory, this W potential. Does this include, for example, this Lennard-Jones?
Okay,
I don't know if that's convex. I'm not
yeah,
sure.
no. Okay, Lennard-Jones has this form. I guess everybody knows.
Because there was a convexity assumption, I remember that.
Okay, so but what is important in Lennard-Jones? You have a is there? Ah, yes. Yes, what is important in Lennard-Jones is the fact that you have a whale. So so this is the important fact. So here there is a repulsion. So this is your lambda, and this is your whale, and the W has this form. So and actually you really need this part. But for the proof, well, I have a proof for this. It's not published, yes. So you can do, for the periodic case, Lennard-Jones plus V periodic, you have the same result, yes.
Because I know that this Lennard-Jones result is related to this Epstein zeta function, right? The minimization of this function is kind of related to the configuration that minimizes this Epstein, or how you call it. This.
Okay, I don't know, but
this is related to. I know some works by Mathieu Lewin, and Leblanc,
okay.
the French people working, I think, in Paris,
okay.
and they work on crystallization, but in an easier setting as here. They just minimize the Lennard-Jones potential in several dimensions, and they try to prove that you get crystallization.
Okay, Lennard-Jones, but no potential, no external
potential.
Ah,
this
okay.
is kind of a more general what you.
Yes, okay. Yes, people are studying, let's say, yes, let's say n particles in the plane, and they want to try to minimize n particles and find the configuration.
Yeah.
Yes. I think it's different, but it's very interesting how to relate the two problems. Well, I don't know, but yes.
Yeah.
It's related, yes, of course, but I didn't know this zeta,
Epstein
function.
Epstein zeta function. Yeah, this is. But I think it's related to the Lennard-Jones potential, to the features of this potential, and then you can relate it to a number theoretical problem, basically, to minimize this, which is in an arbitrary dimension. It's not understood. Only a D is 2 maybe, but if D grows, then nobody knows how to which lattices minimizes this potential.
Okay, thank you.
So,
interesting to study.
Yeah, thank you as well.
So maybe a question to the relation with Lagrangian dynamics, because you mentioned some of these words, I mean Manet, and so I'm not a specialist in this area, but is it just an observation, or does it give you some proof techniques and so on?
No. It's not an observation. It's really a discretization of Lagrangian field. This energy is actually an action here, which means it's not the same dimension, physical dimension. It's time energy. And in Lagrangian theory, you say that your trajectory has to minimize the Lagrangian, and here you say you minimize the total energy. So but it's not just a simple observation. Now, if you want to solve let's say the Hamilton-Jacobi equation, in this theory you want to understand the long time behavior of the, let's say, the Hamilton-Jacobi equation with time, and the long time behavior will be a solution of a cell equation, like in Lyon's Papanicolaou paradigm. And if you want to understand this, you can discretize the time, and you come back exactly to this problem, and it's there is a proof that, let's say, the discrete energy, effective energy, converges, let's say, to let's say, the cell equation where you have to add a special value, which is called, let's say, correctors effective many value also. There is a name for this. And also the solution in time, if you discretize, which means that the xk, which means the x, so if tau is the discretization of a time, you have actually a function x of k tau, and this will give you a path, and actually this could be done also in RD. This would give you the path when tau goes to 0 of the minimizing path, the path which minimizes the Lagrangian. So it's also a theory you have when you want to understand the geodesics, where again you minimize some kind of energy, and but there is no potential for geodesics. You just have a distance to a square, and this is the same problem to minimize to obtain the geodesics, and to show that okay, to obtain minimizing geodesics is exactly related to this problem, or in more generality, if you add a potential, you have the Manier theory.
Thank you.
Any more questions or comments? If not, let's think again. Entra na conta do João. Ah, tá, peraí. Deixa eu ver se é verdade. Deixa eu ver se é a conta dele. Parece que é ele aqui. Tem promoções aqui. Acho que é do e-mail, do João PT. Isso, Maia.joãopt. Acabou de 10 minutos. Maia.joãopt.
Hello. Hello. Okay.
So okay, so just to understand what was the plan for this sequence of talks. So in the first day, if you remember, Lucas gave us some kind of a historical review about the notion of contour in statistical mechanics. So then came Kelvin in the Tuesday, and Kelvin he just discussed the part of his master thesis which he contained new results, which is actually related to this talk here. So then Kelvin explained something that we got also from Pierre Pico, the notion of the compatibility, so on. And then Wednesday, João Maia defended his PDA thesis, which was we used these contours to work on the random field Ising model. So then the plan was to close this sequence of talks with an application of the cluster expansion convergence. So this is so Lucas will more or less explain this paper which we did where Kelvin also is involved and also João Maia. So he will speak about on the decay of correlations for long-range Ising models. And so okay.
Okay. So thank you, Rodrigo. So I'm here again to talk about the actually one of the possible applications of the cluster expansion that Kelvin talked Tuesday. So just for you to remember, we are in the context of Ising systems with a long-range interaction. Okay, so mainly this is the interaction we are talking about the whole week. And what I didn't define during my first talk was actually the notion of the finite volume Gibbs measure, but many of you already know this. And you have these collections of finite volume probability measures that you construct using the Hamiltonian. And for Ising systems, you have two special probability measures that comes from the weak limit of the finite volume measures with the plus or the minus boundary condition. Okay. And there is an important quantity to study in these systems, and this is the truncated correlation function. Okay, that is defined by this. It's just measuring how the spin variables in the origin and x are related. And usually you know that since this is extreme mode, in the limit where the norm of x is going to infinity, this goes to 0. But an interesting question is how fast this goes to 0, and what many physicists expect to happen, and what can be proved in many situations, is that sometimes this correlation decays exponentially. So you can somehow ask yourself if this can be proved always for any, for instance, Ising model. And what happens is that this problem for the nearest neighbor Ising model is completely solved right now. So for the nearest neighbor, there is a quite recent proof that the correlation function decays exponentially for all pairs depending on beta and h. The field here you can consider a magnetic field, a constant magnetic field. It decays exponentially for all pairs, but at the critical value. So this, of course, the problem was completely solved recently, but the question was studied for many years actually, and the first proof of this theorem right here started with a work by Lebowitz and Penrose in '68, where they proved the decay for beta and H when H is not 0. When H is not 0. So the remaining case was the case where H is 0. And then in '87, and Eisenman, Barsky, and Fernandes solved the problem for H equals 0 and for regimes of, or subcritical regimes of the temperature. Okay. And finally, recently, Dominique Copin, Goswami, and Raouf, they solved the remaining case, the supercritical case, and this is it. Well, what happens at the critical temperature is already known that at the critical temperature, by a result of Simon, that at the critical temperature, the correlations cannot decay exponentially, so they decay algebraically, actually. Sorry? Oh, yeah, so this is actually a second, this is published on Communications, but there is a withdrawn version in archive, I guess in 2015, yeah, by Dominique Copin and Eisenman. But this one is published, yeah. So, and okay, so the exponential decay doesn't happen at the critical temperature, and of course, if it happens to the nearest neighbor, it happens for any finite range Ising model. But then you can ask, okay, what happens for the long range case? And actually, at the long range case, it was already known that you cannot have, you cannot always have an exponential decay of the correlations. Why? There is this result by Jagonitz and Souillard, where they show that if you have a ferromagnetic Ising spin system that is long range, then it is. This is published in a physics journal, but it's just a consequence of the GHS inequality. And what you can show is that there will always exist a positive constant, depending on beta and H, where the correlation between X and Y doesn't decay faster than the coupling. Okay. So what this means is that, okay, so if the long range is exponential, then you can still have an exponential decay. But in the case that we are interested in, where the decay is algebraic, then the correlation cannot decay exponentially in any temperature for any magnetic field. So, and of course, there is no restriction on the dimension here also. So, and there is okay. Now you have the lower bound, so it remains to show the upper bound, right? So there is an unpublished paper here by Newman and Spoon, where they solve the problem for the long range Ising model in the subcritical regime. So they can actually show that the correlation is asymptotically has this expression right here, where this key beta is the magnetic susceptibility, okay? And this it's asymptotic in X. So when the norm of X becomes large, then you approximated this expression right here. Okay, so what remains? Okay, so what remains is the regime of temperature where you indeed have phase transition. So we go back to the one-dimensional systems where the theory is more developed, and there is some important papers. The first one by Imbri that we talked about, also Pico talked about in his talk, where they developed where the strategy here is to develop a cluster expansion, and then he can show that the decay of the one-dimensional long-range Ising model with these coupling constants decays as something like this. So with the right exponent. And what he actually studied a few years later with again with Newman is that something new happens in the case of long-range system, is that when you are getting closer to the critical temperature of the model, the upper bound, this upper bound doesn't describe anymore what's happened to the correlations, and what you actually get is a decay that is dependent on the temperature, and they prove this for this kind of system. So, and this they use different techniques here. So, and also to set another important result, there is the result of Luis Renato is here, and also Pico talked about this, where he studied the decay of correlations in an extension of the model now living on the continuum, and then also studying decay of correlations. There is the paper by Cassandro, Pico, Merola, and Rosikov, where they study where the strategy is the same as. When I say the same, I mean using cluster expansions. So you use cluster expansions, and then you get also the decay of correlations, but in this case they have the decay of the anypoint correlation function as well. So following this thread of results, there is our result. In this case, that is a paper in preparation, okay? And part of the result Kelvin already talked about. I will only talk about this case. There is a corollary of the cluster expansion that says that there will be a constant depending on alpha and d, okay? Such that the correlations decay as the coupling constant, okay? So algebraically with the right exponent alpha. So just to remember, the idea is to use the cluster expansion, and as Kelvin talked to us, you have this expression for the free energy, okay? Where this function here, this phi t, have this expression right here, okay? So this is a sum overall connected graphs, okay? Actually, yeah, exactly. And then you sum a product of this complicated stuff that have a dependence on the compatibility condition that Kelvin talked about. So we are interested in an upper bound. So essentially, we don't need to remember what exactly this expression for the activity is. What we do need to see is the quantity that we need to control, and is this modified activity here. We can bound this the absolute value of this by this quantity right here, and this quantity right here is again complicated. You have something that many already expected: the exponential of the minus the weight of the contour. This is a modified weight of the contour. And then you have here also an expression depending on the sum of all the trees of a really complicated expression. So what happens in the cluster expansion for the long range systems is that usually in the finite range case, you only have some complication coming from here, that you have these trees only coming from here. But now the activities also have trees. That there is also a sum involving trees over here. So, and just for you to remember, the trees right here, they represent an interaction between the contours given by an expression like this. So just an interaction between two different contours in a given polymer. So when you do some density calculations, what you get is an expression like this. So you need essentially to control a series that looks like this. So you have the modified activity, you have the absolute value of that difficult function that I showed you before, and some other constants. And the important thing is that since you are studying the correlation between X and Y, when you do the calculation, you just need to restrict to see what happens when X and Y are contained in the volume of the polymer. So the first thing is that you can bound that's something that is complicated by another sum with trees here. So you have two rounds of trees, as I said. You have trees over here, hidden right here, and you have trees over here. So what is the strategy that we use? I want to recall a little bit the strategy of how do you show the convergence of the cluster expansion in this case. So first, since you need to control a series, you can break the series into level sets depending on how much elements you have in a given polymer. And if you can manage to show that this quantity right here is bounded by something like this, if beta, since this term right here goes to 0 with beta, then for beta large, you get that each term depending on n is small, and then you take the power n, and then you can show it to converge. But how do you show that this indeed converges? So the strategy is, since you have this sum over here, you have to deal with sums that depends on trees. Okay, so this will give sums that depends on trees, and the vertices of the trees will be the polymers at X, okay, and the edges will be given every time that two polymers are not compatible. So in order to control it, you need to have a control of this quantity. So this quantity says that you can indeed control the sum of all the polymers that are not compatible with a fixed one. You can control it using a term that goes to 0, okay? M is a constant that is fixed in the construction of the contours, okay? And there is a dependence on the mass of the given polymer, but since the mass is something that only the previous weight cares about, so you can easily kill this term during the computation. So what is the computation? Usually you have, again, a sum over trees. So at each point at each ball over here, there is a polymer, okay? And they are connected if they are not compatible, okay? So the idea is to reduce the bound in a given tree by summing over, giving a polymer, summing over all of the edges that are connected to this polymer. This means using this bound over here. So when you do this, you get a smaller tree, and then if you iterate this procedure, eventually you reach at some point that has only one polymer, and then you have to care about only what happens to this case. And now there is the second round of sums over trees, but the strategy is again the same. So you break it into level sets. Again, this modified activity contains the sum over trees, and then now in this case, the condition is that there is an edge between the contours if they are compatible in the sense of contours. So there is a change on the notion of compatibility to control this sum over here. So what do you need to do? Again, the same thing. I guess Kelvin proved this exactly, right? In his talk. But the strategy is similar to the one I told you before. You need to, given a contour, to control what happens to this kind of sum, that is essentially summing the contribution of the contour weights that are coming from every contour that is somehow connected to a given gamma zero fixed. And in this case, the bound is also given in terms of something that depends only on the previous generation, the generation gamma zero. And then you also get a constant C beta over here, and C beta has the nice feature of, again, only depending on alpha, D, J, and M. And when beta goes to infinity, this constant over here goes to 0. Okay? So, again, going back to the problem. Now, you need to show the series that we need to control is this one. So, in order to control this series over here, there is actually two possibilities. Since we are asking that x and y are inside the volume of the polymer. So the possibilities are if the pair is inside only one gamma, only one family of contours, or if they are into two different polymers. So I will just show the strategy for this case over here. Okay, I will just show the strategy for this case over here. So I will just bother you with the details of one summation over 3. So now we have a different situation here, because consider this a general tree, but for this activity right here. So since we are saying that x and y are inside the volume of gamma, what may happen is that x and y can be into different vertices of the tree. So what you do first is that by the same arguments previously done, we had only one point of the tree that was fixed, okay? Now we have 2. But by similar arguments, you can sum over all the other edges here, okay? And chopping this tree to something that will only depend on x and y. So by similar arguments, you can chop your tree to give you something like this. And this is the case for two-point function. Actually, if you have an n-point correlation, this gets a lot messier, okay? So now you have only a tree that is essentially a line, okay? So you need to control this. The strategy is a procedure that I called erasing edges. So somehow you need to erase these edges and to bound the sums over trees that are lines like this, okay, into trees that are that have only x and y. This will be easier to control. And what you do is that there is a nice lemma, and this lemma, if I define f of a and b as the interaction between the sets a and b, what I can actually do is that I can bound the product of 2 of them with b being the same in the 2 of them by something that depends only on b, kill with an exponential term, okay? Some terms depending on the distance, but here I have the interaction term between. Okay, this is wrong. This should read A and C, okay? A and C. So what you are effectively doing is that you are erasing an edge, a contour that is between two edges, and substituting by the edge between the fixed contours. So the idea of the proof is quite easy. You just compute the product. You get something if you divide and multiply by the coupling constant containing the interaction between A and C. Then you just need to take care of this quantity over here. And then you can use, you can easily use the triangular inequality and some easy bounds with the distance gives you the desired result. So how do you effectively erase edges? So suppose that your graph only have gamma 1, gamma 2, and something in between. So what you do is that when you try to compute that sum on the activities, of course, you have another sum depending on gamma 1 and gamma 2 with the weights, but there will be the sum depending on the contour in the middle of them. So you use that bound that I showed you before, and since the diameter of the contours are exponentially bounded, you get an expression that's quite nice. And then you can show that this quantity right here can be bounded by some constant C beta, where it goes to 0. It also goes to 0 when beta goes to infinity. And now you change this edge, this sum on the vertex in the middle by something that goes to 0. There is a small times the edge between the points, okay, the extremities. So what remains to do is that you need to sum over all possible trees that are lines, okay. So for each n, you have a sum that for contours that are aligned like this, but with the restriction that x is in the first one and y is in the last one. By iterating the procedure that I showed you, you get something like this, okay. And then by a trick, you can show that only one edge can be bounded by something that depends on the size of the contours of the diameter, but the diameter is at most exponential, and the coupling constant between x and y. So then you get the desired result. So the conclusion is that, okay, now you get the decay of correlations for the very high case of temperatures, but you can ask what happens closer to the critical temperature. So in that paper by Imbre-Newman, they found very different behavior for the correlation function when you are becoming closer to the critical temperature. But this was done only for one dimension and alpha equals to 2. So I don't know if it is expected to happen for any long range. I don't know. One dimension and alpha equals to 2. This paper right here by Imbre-Newman. Yeah, just for the case of alpha equals to 2. Oh, they don't. Yeah. So this is the first difference between the other case. Yeah. Yeah. So yeah, just relating the decay. What is the exponential? Maybe for alpha between 1 and 2, I don't know if you expect it to be constant until the critical temperature. I don't know. Yeah, because yeah, anything can happen. Yeah. So there is also I only talked about the decay of the 2-point functions, but in Pico's paper there is the decay of the any-correlation function, so you can also try to study this. And as I told you, in the case that you have any fixed points, the procedure of chopping trees that I showed you are quite messier, so this is expected to be harder. There is another thing that happens in the paper of Pico, in the cluster expansion paper, where they studied the distribution of the phase separation point. Okay, and you can ask, since we have cluster expansion, you can ask if something similar can be done for high dimensional models. But in this case, you are not studying the fluctuation of one point, but of an interface. Okay. And there is another important question that I didn't mention, is that the GHS inequality works for when the field is positive, okay? So that result that I showed you of the decay of correlation, it happens when the field is positive. And it's not true in general that any long-range system will have a decay that is algebraic. Actually, there is a very important paper by Bridges called studying something that they call Debye screening, where they show that if you have a Coulomb system, so essentially a long-range system, then the decay in some regime can become exponential. So, but the main difference between that system, the Coulomb system, and the long-range ferromagnetic system is that you have many changes of sign in the interaction. But now, if you put a random field, then the field can have any sign. So maybe this can can conspire to give another answer for the decay of correlations. But of course, this is only speculation. We don't know. So thank you.
Thank you very much. Just about the last mention, what's happened with the random field. I think that there's a paper by Leuzi and Parisi,
okay,
where they did something like this for the random field. They make a simulation, but it's a kind of slightly different model. But they study this problem. You can ask to Parisi or to Leuzi what they think about this.
Oh, what they think about this?
Yes, yes.
What
He
happens?
will answer you.
Okay.
You say that I told you to ask.
Okay, I will send him this email.
So he will answer in this case. Okay, about the phase separation, something that could be at least easier than studying the wall form of the interface. Because a priori it could be more rigid. If you are in 2 dimensions, if you have a long-range interaction, it could be, it's not clear that you have the same fluctuation that you have for the short-range model.
Oh, yeah.
It could be a lot more rigid, okay? So we have to be careful.
Okay.
And first thing that you can try to do is to consider just you take a symmetric volume, okay?
Okay.
And you look at the position of the separation line at the origin.
Okay.
To see how if this one is not if this one is not moving, you know. Okay, so it could be a criteria for no, because what we did for the phase separation model that we discovered with a surprise that the distribution for the center for the O phase separation point is the same that in the Ising model and 2 dimension when you look at the middle of the volume and you look, it's exactly the same distribution.
But in also alpha equals to 2 is the same?
Yes.
Yes. Oh, nice. Yeah.
No, it's the same. I mean it is a, no. Sorry, alpha equal to 2. We didn't do that for the other case. But okay. This part, I mean, the distribution for the Ising model and the center of the point, there is an exact computation by Abraham and somebody else, I forgot. But it is very classical. Abraham and... You remember? Abraham and Reed? Abraham and Reed, perhaps.
Abraham and Reed. Okay, I will...
Yeah, it's mentioned in your paper.
Okay, so...
So you can look at that. Okay, for the random field, I don't know. I have no idea. But for example, the question could be, I mean, a completely different question could be in the same spirit. What's happened if you have an antiferrometric model?
For the decay, yeah.
Yes, we don't know that.
Yeah,
I mean,
exactly. Yeah. Even in
long
one
range
dimension.
and antiferromagnetic.
Even in 1 dimension.
Yes.
Okay.
No, because I mean, okay, I would have to speak also about the first part, about investigating the regime closer to the critical temperature. Okay.
Oh, okay.
There, a priori, there's a difficulty in the Imbri-Newman paper Okay, so they make something very strange. I mean, okay, a part of to prove what they want to prove, a part is using Fortran Castor and representation, and the other part is to use cluster expansion. Unfortunately, for making the cluster expansion, they need that the nearest neighbor interaction could be arbitrarily large. So they don't really prove what they say. They say, okay, there is a model which is similar to the case, but with short-range interaction, which could be as big as you want to get the convergence of the cluster expansion. So this is a kind of strand. This I don't like it. I can tell you that something could be done for that. I mean,
Okay.
And the program could be to try to get in one dimension long range to get, I mean, the cluster expansion that converge until the critical temperature. Exclude.
Okay.
You can do that. Anyway, in more than one dimension, okay, there's also a problem that comes from the what's called completely analytic potential. Something.
Okay.
I mean,
by Dobrushin
and Schlossman. Okay. So with Enzo Olivieri, we did something in 2 dimensions, in D dimension. So about this kind of problem. I mean, to replace the problem of the fact that you say with cluster expansion, it's converging when beta is smaller than something.
Okay.
More larger, perhaps. And not smaller because we are from the small temperature. Okay. What's happened is that it's not very clear if some criteria could be done for long-range model.
In the spirit of
in the spirit of completely analytic potential and etc. There could be also something interesting to do in the sense that you want to define the convergence of the cluster expansion in terms of some finite property that a priori could be computed with a computer.
Okay.
So you write abstract condition. Huh? Okay, and it could be interesting to make the case, consider the case with long range. I have some reference for that if you want. I mean, a student of Olivieri tried to do this, but I'm not sure. But then you wind up, okay, disappear. But we can find something. That's all.
Yeah. Okay. Thank you.
Yeah, for the phase separation problem, it would be, I also think, would be very interesting to study the existence or non-existence of Dobrushin states, you know, that you get by putting plus boundary conditions on upper half of a box minus on the lower of a box. Am I right that there are no results about this?
No, actually there are results by Van Etter, I guess Leni and Lauren Coquille.
About the existence of long range
Dobrushin states. What they actually show is a paper, I guess, on Journal of Statistical Physics. What they show is that the Dobrushin states cannot generate something that is not translation invariant. But they have not only this model, but they have different also models. They have different long range cases. Like they have a long range that is anisotropic. They have a long range, this long range, and they have, I guess, at least 3 models where they can study.
But is it known that in 2 dimension, which would be 1 dimension more than the dimension where you do have a phase transition? So let's say in short range, you have a phase transition for Ising model in dimension equal 2. In 3 dimensions, you have Dobrushin states. Is it true that in dimension 2, for the long range model,
if there is
no, it's not known.
No, not known. No, they have this model to produce a Dobrushin state. They put what happens essentially is that the decay in 2 dimensions in this case where the interaction is isotropic, so so you don't have a difference between the direction where you are interacting. Okay, so in this case the decay is too fast in their paper. So what they managed to show is that the Dobrushin states, the Dobrushin boundary condition cannot produce a non-translation invariant state. This is what they show. Than D. Bigger than 2. Alpha is bigger than 2 because the dimension is only 2. And but what happens is that we have actually we have the following situation. There is about the phase diagram in these models. It is already known that the translation invariant Gibbs measures are only convex combinations of plus and minus. This is already known. But it is not known if at least in 2 dimensions for this case, if any Gibbs measure will be translation invariant. And this is relates to your question. And what Van Etter showed is that the obvious candidate to generate a non-translation invariant, and the obvious one is the Dobrushin boundary condition, does not generate a non-translation invariant state for this model. So, but they cannot exclude some other kind of strange boundary condition. And since in this case you see long-range systems are quite different. So I don't know what to expect in 2 dimension. Maybe if you have some strange boundary condition, you can produce it, but I don't know.
More questions or comments? No. So let's thank Lucas again.
Oh, I just clapped for myself. Oh, sorry, I'm just crazy.
You are
yeah,
very good,
I'm
Lucas.
very crazy.
Even
Yeah,
you
no,
recognize this.
sorry.